Now come to the next point, mutual induction. So as the name itself suggests, here we are talking about the mutual phenomena of induction. So what does it mean? So in this case we can say if two coils, let this is one of the coil and another coil is this, and when these two coils are kept very close to each other, okay, let the name of these coils are coil number 1 and coil number 2. So what is this phenomena? Suppose if current in one of the coil is there, due to that current there is a flux through the same coil, that's okay, but the magnetic lines of forces will pass through the second coil also. Let for example, if I1 is the current in the first coil here, so due to this current here, magnetic field lines can be go in this direction. It can have like this. So lines of forces will pass from the coil 2 also. When lines of forces are passing through the coil 2 also, so there is a flux in the coil 2 due to the current in coil 1. So if current in the first coil changes, so flux in the second coil will also change. Due to the change in flux in the second coil, there is an EMF developed in the second coil, and this phenomena is called mutual induction. So what we can say, the induced EMF in the second coil due to change in the current in the first coil called your mutual induction. So we can write here like this: when two coils are kept very close to each other, and if current is flowing in one of the coil, say here coil 1, then there is a flux through the coil, through coil 2. That flux is called, mutual flux. If current in coil 1 changes, then the mutual flux of coil 2 also changes. Mutual flux of coil 2 also changes. So that change in the flux, so the change in flux through coil 2 produces induced EMF. In the coil 2. So we can write. So phenomena of phenomena of induced EMF in coil 2 due to change in current in coil 1 is called mutual induction. It means mutually, that EMF induced mutually here. So let current in coil 1 is I1. Then mutual flux in coil 2 due to current in coil 1 is directly proportional to current in coil 1. We can write phi 2 1 flux in current 2 due to flux in coil 2 due to current in 1 proportional to I1, or we can say phi 2 1 is equal to M into I1. So M written as phi 2 1 by I1. So where M is called M is constant called coefficient of mutual induction, and this can be written like that also, or we can say change in flux in coil 2 due to current 1. The rate of change in flux in coil 2 due to current in 1 is directly proportional to dI1 by dt, the rate of change of current in the coil 1. So further, this also written as d phi 2 1 by dt is equal to M dI1 by dt, which further written as here M is equal to your d phi 2 1 by dt. That can be said as your minus E21 by dI1 by dt. This is the mutual induction. M also we can write M is equal to your modulus of minus E21 by dI1 by dt. So either in this manner we can define the coefficient of mutual induction. M is equal to mutual flux by current I1, or we can define like that induced EMF, mutual induced EMF by rate of change of current in the another coil. Similarly, by theorem of reciprocity, by theorem of reciprocity, if I2 is the current in coil 2 and mutual flux flux in coil 1 is phi 12, then phi 12 is proportional to your I2, or we can say phi 12 is equal to your Mi2. So M can be written in that form also. Just reverse process. M is your phi 12 by I2, or M is your phi 21 by I1, and this further we can write modulus of E12 by di2 by dt. So either we can define in this manner or this manner, both have the same meaning. Only we have to consider by question to question or problem to problem in which coil we should take current, so that we can get the more accurate or exactly accurate value of mutual flux through the coil, another coil. Now M, what about M? M is very similar to the coefficient of self-induction. So we can write M is here, some point related to M we can write. Now see the first point, mutual inductance. Mutual inductance M is scalar physical quantity with SI unit is Weber per ampere or Henry, same as the SI unit of self-inductance, and its dimension M can be written as dimension of flux by dimension of current. Flux is your B into area, B is your F by IL, F into S by I square L. Now, dimension of M can be said dimension of F, ML is ML minus 2, dimension of M is F is your ML T minus 2L square A square L. So finally we can write M L square T minus 2A minus 2. This is the dimension of mutual inductance. Second point, mutual inductance depends on geometrical shape and size of both the loops, depends on geometrical shape and size of both the loops, and the medium between the loops. So mainly here mutual inductance depends on geometrical shape and size of both the loops as well as medium between the loops. Now see how to calculate the mutual inductance if we are having certain pair of coils are given here. See, now calculation of mutual inductance. Let first one of the case in which we are taking two concentric circular loops, two concentric circular loops of radius r and small r are kept and having number of turns capital N and small n respectively. Find the mutual inductance between them. Mutual inductance between them. So this is the question here. So we are having two concentric circular loops. One having very bigger radius, another your very small radius like this. Let this your bigger one. And in this your number of turns are given your n. Capital R, number of turns your n. And then we are having very small loop and number of turns your small n. So these are the two loops kept concentrically. Outer loop have radius capital R, inner loop have radius small r. Now we want to find the mutual inductance between them. So first of all, see, mutual inductance if you want, so that is your either phi 1 2 by I2, flux on coil 1 due to current in the 2 by I2, or we can say phi 21 by I1. So first of all, we will define the two loops, which one has 1 and which one has 2. Anyone you can say 1 and 2. Let this is your coil 1, this is your coil 2. So important point here, in which loop we should assume a current. See, if we are assuming current in the outer loop means coil number 2, since then we want flux through the coil 1, and coil 1 is very close to the center of the coil 2. Both are concentric and radius of that is also very small as per the given condition. So we can say whatever the magnetic field produced by the coil 2 at the center, everywhere inside the coil 1 we can assume a uniform magnetic field. So this is the one of the possibility. You can take a current in the coil 2 and then calculate the flux in the coil 1, and that flux will be called as a mutual flux phi 1 2 by I2. Now if we want to do just reverse that, so if we are considering current in the coil 1, then inside the coil 1 magnetic field we can get, but here because when we want the flux to the coil 2, we want flux to the whole area, inside as well as this part. But here it is difficult to calculate the magnetic field because that is our beyond the limit, beyond the syllabus. So we can say we would like to prefer taking current in the coil 2 and then flux in the coil 1. So let current I2 in coil 2. So magnetic flux through coil 1, that is called flux in the coil 1 due to current in the 2. That can be written as first magnetic field to the coil 2 mu naught by 4 pi I2 by R into 2 pi and number of turns on the outer your capital N. This is the magnetic field. Area of the inner coil. Inner coil have area pi r square and number of turns small n. The total area will be your pi r square into small n. So m is your 512 by I2 divided by I2. 2 pi here cancel. So you can say mu naught by 2. And here we will have small r square by capital N small n into small r square by r. So this is the mutual inductance between the coils. So from here we can say it depends on the number of turns on the bigger one as well as number of turns on the smaller coil. Similarly, radius of the inner coil and radius of the outer coil. So we can have mutual inductance depends on geometrical shape and size of both the coil as well as medium between the coils. Now see another case here. A long circular coil, a long solenoid and circular coil is kept coaxially as shown in diagram. As shown in diagram. So diagram is like this. Let this is your long solenoid of radius your R1 and this is your circular loop of radius R2. Long solenoid and circular coil is kept coaxially as shown in diagram. If R1 is the radius of solenoid and R2 is the radius of the circular coil, is the radius of circular coil and small n is the number of turns per unit length in solenoid and capital N is the number of turns on circular coil. Then find mutual inductance between them. This is the case here. Now same method here again. The mutual inductance M is again 512 by I2 or 521 by I1. So first we will define 1 and 2. Let circular coil is your coil 2 and solenoid is your let coil 1. So if we will use current in the coil 1 means solenoid, so flux through the coil 2 means circular will be only from this region. So it is very easy and convenient to find mutual flux in the circular coil if we are considering current in the solenoid. So that's why we should take current in the solenoid. So let I1 is the current in solenoid, then magnetic field due to this solenoid, then magnetic field on the axis of solenoid is B is equal to mu naught N I1. Now, then mutual flux in the coil 2. Then mutual flux in coil 2, that means phi 21 written as magnetic field mu naught Ni1 into area. Flux only by this area only. So pi R1 square, and number of turns on the circular coil is your capital N. Capital N. So this become your mu naught into pi small n capital N into R1 square into I1. So M is equal to your phi 21 by I1, and which will be here mu naught pi N capital N into R1 square. This is the mutual inductance between the solenoid and circular coil, mu naught pi N capital N into R1 square.